Any linear programming involving two variables can be easily solved by graphical method, as it is deal with the two-dimensional graph. But if the decision variables x, y greater than 2, greater than means if the decision variables are greater than 2, and if we solve by graphical method, it becomes very complex. An American mathematician G.B. Danzig was developed a method known as Simplex for solving linear programming problem. So if the problem maximization of z is equal to 4x1 plus 10x2 subject to the constants 2x1 plus x2 is less than equal to 50, 2x1 plus 5x2 which is less than equal to 100, and the third constant x1 plus 3x2 which is less than equal to 90. To solve this problem by Simplex. Now I will discuss how LPP can be solved by Simplex method. First of all, for putting all the values in the table, first we write this LPP in standard form. So in standard form, here less than equal to type, all the constants are less than equal to type, we have to introduce slack variables. So in the first equation, 2x1 plus x2 means it is less than equal to, means if we add a real number which is greater than equal to 0, then this inequality becomes equation. Similarly, in the second constant 2x1 plus 5x2 plus s2 which is equal to 100. Similarly, in third x1 plus 3x2 plus s3 equal to 90. Now this canonical form in its standard form. So first step is you have to write in the problem in its standard form. Now the Simplex method is an iterative method. So it can start with some starting solution. So in this case, it is an iterative technique and we have to find maximization of the z function 4x1 plus 10x2. We have to start some basic feasible solution. Here, if x1 equal to 0, x2 equal to 0 and x3 equal to 0 gives s1 equal to 50, s2 equal to 100 and s3 equal to 90. Obviously, if you put 0, 0, that means s1 equal to 50, 0, 0, s2 equal to 100, 0, 0, s3 equal to 90. And the problem maximization of z 4x1 plus tan x2. We add some slack variables, therefore the coefficient of slack variable in the objective function we have to write 0, 0 and 0. So it gives z equal to 0. If we start 0, 0, 0, where x1 equal to 0, x2 equal to 0, x3 equal to 0, the max z equal to 0. Now we have to find maximization of z. So we can start by taking this as an basic variable. How we put all the things in the table? First we have to write the coefficients, the decision variables and the coefficients x1, x2, s1, s2 and s3. And here we start s1, s2, s3 as a basic feasible solution. We have to write here s1, s2, s3 and we have to write here the coefficient of objective function, means in z. So the coefficient of objective function x1 is 4, the coefficient of x2 is 10 and the coefficient of s1 is 0, 0, 0 and the coefficient of s1, s2, s3 is 0, 0, 0. We have to write here coefficient of basic variables. Here it is known as basic variables and this is coefficient of basic variable from the objective function. Here it is a coefficient of objective function now x1, x2, s1, s2, s3 and s1, s2, s3. Here now we have to write the equations in the first form. The x1 coefficient is 2, x2 1, s1 is 1 and there is no s2, that means here 0 and no s3 in the first constant, so s3 and the right hand side 50. Say it's a solution, means 2x1 plus x2 plus s1 equal to 50. The first constant it written as. The second similarly 2, 5 and there is no s1, so it is 0 and s2 coefficient 1 and 0. There is no s3 in the second constants and the 100. The third one, coefficient of x1 1, 3, 0, 0, 1 and the left hand side is 90. So the first step is we have to write in its standard form and for the simplex method we have to start some basic variable s1, s2, s3 to find maximization of z. Here the maximization of z is equal to 0. Now we have to improve this solution with starting variable s1, s2, s3 as 0, 0, 0. It is the coefficient of maximization of z. So now we have to calculate here zz. What is zz? Zz is a dot product of, suppose z1, it's a dot product of 0, 0, 0 to this column. Means the first 0 into 2 plus 0 into 2 plus 0 into 1. So it is 0. Similarly, for finding another column, we have to dot product this to this plus this to this plus this to this and write here. So it is 0. Similarly, for x2, 0 into 1 plus 0 into 5 plus 0 into 3, this gives 0. Similarly, so if you look carefully, the basic variables are in the left hand side. That means we have an identity matrix in that table. Here S1 is the first basic variable, so here first, and all the remaining are 0. Similarly, S2 is the second basic variable, so here in the second, here 1, and all are zeros. And S3 is third basic variable, so the coefficient of S3, it is in I. So if we look at 3, 3 matrix, here coefficient of S1 1, S2 1, S3 1. So it is an identity matrix in order S1, S2, S3. So S1 equal to 50, S2 equal to 100 and S3 equal to 90 gives the objective function is 0. Now we have to improve the result of objective function 0 to further. So for this we have first to calculate Cj minus Z. Here Cj is the coefficients of objective functions. Cj is coefficients of objective function respectively. So for this column C1 minus Z1 means C1 is 4 and Z1 is 0. Here 4 minus 0, it gives 4. 10 minus 0, 10, 0, 0, 0. For improving the result further, we have an optimal criteria. What? We have to choose the maximum value among them. We have to choose the maximum value. The criteria of optimality, when the finished criteria is Cj minus Zj, which is less than equal to 0. Here 4 and 10 are positive, it doesn't satisfy the criteria of simplex. For going further, we have to choose maximum among this value. Here 10 is maximum. So here 10 is maximum among them. So x2 will enter. x2 enters. But which one leaves? For doing which one leaves, we have another find, the ratio. To find ratio means this is our key column. We have to say this is our key column. Key column. Ratio means the 50 by 1 gives 50. 100 by 5 it gives 20, and 90 by 3 30. We now know x2 enter, but which basic variables are leave. So for this, here we choose maximum among them, here we choose minimum among them. Here the minimum value is 20, so corresponding 10 and this row here x2 will enter and s2 leave from the basis. Here the first basic variables are s1, s2, s3. Now s1 we rewrite again similarly. S1, as it is not leave, s2 will leave. In place of s2 we have write x2 and s3. As I already told, and the coefficient of s1 is still 0, the coefficient of x2 in the objective function is 10, and the coefficient of s3 in objective function is 0. As we have seen s1, s2, s3 and the identity matrix form in the way where these are introduced. Here s1 is already there, x2 is introduced, means the coefficient of s1 here 1 and coefficient of x2 in here must be 1. So now we have applied the Gauss-Jordan elimination method to change row equivalent form from s1, s2 and s3. So for doing this, what we have to do, if we have to put s2 and x2 here 1, for this we have to divide the equation divide by 5. So what s2, now here s2 which is s2 by 5 and here this is give x2. So we have to divide by 5, this is 2 by 5 and 5 divided by 5 1. This is our purpose here to put 1, that's why we divide by 5 and it is 0 and here 1 by 5, here 0 and 100 by 5 is equal to 20. Now for the value here is 0, when it becomes 0 we have to change row equivalent form or applying Gauss-Jordan elimination method. Here it is 2 1 1 0 0 minus, if we subtract 1 minus 1 it gives 0 here, means what, simply minus 2 by 5 1 0 1 by 5 comma 0. If we subtract this equation by this equation we have 0 here. Similarly 2 minus 2 by 5, it's 2 minus here, it's 2 minus 2 by 5 which is 8 by 5. 1 minus 0, it is 0. 0 minus 1 by 5, it is minus 1 by 5. And the 0 minus 0, it is 0. Similarly for solution, 50 minus 20, it gives 30. So what we are doing, we are changing its in by applying Gauss elimination method. Now it becomes 0 and it's already 1. Similarly, our aim is here we have to write 0 by changing row operation. For this, what we have, so the column is 1 3 0 0 1 minus, if we multiply by thrice in that equation, then it gives 0 here. So 3 thrice time 2 by 5 1 0 1 by 5 comma 0. So what will happen? 1 minus 6 by 5, it's minus 1 by 5. 3 minus 3, it is 0. This is our aim. That's why we changing row operation in that form. 0 minus 0 0. 0 minus 3 by 5, it's minus 3 by 5. And 1 minus 0, it's a 1. Similarly, 100 minus thrice time 20, it's give 100 minus thrice time 20, it gives 40. So our aim is for changing this key element to 1 and the corresponding column to 0 by applying Gauss-Jordan elimination method. Now, if you look carefully here, S1, the column introduces 1 0 0, that is S1. S2, the corresponding column is 0 1 0, and S3, it's already 0 0 1. Means we have again formed an identity matrix in S1, S2 and S3 in the simplex step. Here, for moving further, as we already calculate Zj by coefficient of very messy variable dot product by column vector. So here, similarly, Zj is 0 into 8 by 5, it's, and 10 into 2 by 5, it is 4. 0 into 0 plus 10 into 1 plus 0 into 0, that means it's 10. 0 into 1 plus 10 into 0 plus 0 into 0, that means it's 0. 0, 2, and this is 2. Similarly, 0, 0, 0. Similarly for the solution, 0, 20 into 10, 200 plus 40 into 0, that gives 200. Now we check the optimality criteria Cj minus Zj. For optimality criteria, we have to calculate Cj minus Zj. For Cj minus Zj, here 4 minus 4, it gives 0. C2 minus Z2, 10 minus 10, it's a 0. It's a 0 minus 0, it's 0. 0 minus 2, it gives minus 2. And 0 minus 0, it gives 0. Now, in the case of maximization problem, we have to check this is optimal criteria is. So, or if you look Cj minus Zj, all the Cj minus Zj, it is less than equal to 0. Here 0 satisfied, 0 satisfy the criteria, 0 satisfy, minus 2 satisfy the criteria, is also satisfied. All the Cj minus Zj is satisfied the optimality criteria. Means we have reached the optimal value. Means this is the final form of simplex. Means this is the final iteration. Why it is final? Because the optimality criteria is for maximization condition all the Cj minus Zj which are less than equal to 0. Here all the Cj minus Zj are less than equal to 0. Means we have reached the final iteration table. So the solution is x2 equal to, the solution is x2 equal to 20. The only basic variable x2, that means x1 is not here written, so that means x1 is 0, and the solution z is our 200. So this is our solution, x1 equal to 0, x2 equal to 20 and z equal to 200. From the table x2 equal to 20 and z equal to 200, and also x1 equal to 0 and x2 equal to 20, it gives z equal to 200. This is the approach for simplex table. If we look again, the problem is of maximization type. Maximization z equal to 4x1 plus 10x2 subject to the following constants. What we have, the first step is we have to write this form in its standard form. Now for applying simplex method, we have starting basic feasible solution. For this, if we have x1 equal to 0, x2 equal to 0, it gives x1 equal to 50. Similarly, s2 equal to 100, s3 equal to 90. And the maximization of z is equal to 4x1 and 10x2, and we already introduced s1, s2, s3. So maximization z is equal to 0 s1 plus 0 s2 plus 0 s3. So if we put all the things, we have find z equal to 0. Since simplex method is an iterative approach, so we start some basic feasible solution and improve the result. So for doing this, we have make a table where x1, s2, s1, s2, s3 are written in that way, and our basic variables here s1, s2, s3 are written in left hand side. These are the coefficient of objective function, and these are the coefficient of basic variable in the objective function. We have write all the values in the table. So this is our second step. We make a table and do all the things in the table. Now we have to find Zj and Cj minus Zj. Zj is nothing but it is a dot product of base coefficient of basic variable to the columns. So Z1 is equal to 0 into 2 plus 0 into 2 plus 0 into 1, it gives 0. Similarly, Z for Z2, 0 into 1 plus 0 into 5 plus 0 into 3, it gives 0. Similarly for other columns. So if we look here, there is no x1, x2. That means if x1 equal to 0, x2 equal to 0, the objective function is 0. Now for improving the criteria for optimality, if to find Cj minus Zj. What is Cj? Cj is a coefficient of all the objective function. So for C1 minus Z1 means C1 minus Z1, it gives 4, 4 minus 0. Similarly 10 minus 0, 10 for other. Check this is the optimal table or not. For doing this, we have to check Cj minus Zj is less than equal to 0. But here 4 and 10 are positive value occurs. So this is not the optimal value. We go further. For going further, we have to check among all the Cj minus Zj which is maximum value. So here 4 and 10 are positive value. So here 10 is our maximum value. So this is our key column. So this is our key column, means x2 will enter it surely from by Cj minus Zj less than or equal to 0. For maximum criteria, it gives x2 will enter. But which basic variable leave? For leaving values, we have to find a ratio from the key column, that is 50 by 1, 100 by 5 and 90 by 3. Which variable will leave by choosing minimum value among all the ratios. Here 20 is the minimum value. That means the corresponding, the cutting value from this and this, here it is 5. So x2 will enter and s2 will leave for sure. So going next table, we have s1 is already here. So in place of s2, we have write x2 and s3. Now applying Gauss-Jordan elimination method, and since from this table we have seen the coefficient of s1 is 1 0 0, the coefficient of s2 is 0 1 0, and the coefficient of s3 is 0 0 1, means an identity matrix form. So for identity matrix, we have to, by dividing by 5, we have make this to 1. So we divide all the values, divide by 5, we got these values. Now the corresponding column have to 0. For doing this, we have some apply row form, row reduced by this column, this rows minus the new values. Similarly, we have to find here 0. Similarly, for making 3 to 0, we have applied by reducing R3 minus thrice time new x2. So now we got 0 here. For in the solution also we have reduced the row form. Now we have checked again Cj minus Zj. For Cj minus Zj we have write again Zj. So Zj is 0 into 8 by 5 plus 10 into 2 by 5 plus 0 into minus 1 by 5, it gives 4. Similarly for Z2, Z3, Z4, Z5, and similarly for the solution, 0 into 30 plus 10 into 20 plus 0 into 40, it gives 200. We check this is optimal criteria or not. We reach optimal criteria, optimal table, we have to find Cj minus Zj, and we have seen all the Cj minus Zj are less than or equal to 0, means we have reached the optimal table. And once we reach the optimal table, then the solution is x2 equal to 20, and x2 is the basic variable, x1 is not in the basic variable, that means x1 is 0, and the solution z equal to 200. This is the approach for simplex table.